So when I graph a thing, where you ask to graph a thing, it feels very weird talking just to one person, but it's all right. Oh, yeah, you know, two. So there's one student. You guys on Zoom? When you're graphing a thing, typically here's my kind of list of things I look for. I'm gonna look for my intercepts. So x and y. I'm gonna look for asymptotes, both vertical and horizontal, and maybe slant, depending on if it's an asymptote. Usually you don't, I mean, it's possible to have one horizontal and one slant asymptote. That doesn't usually happen. Usually it's horizontal or slant or neither. And then I typically look for what I call the first derivative stuff, meaning I'm going to find where it's increasing or decreasing and any possible extrema. And then I look for the second derivative stuff. Which is going to be where the function either concave up or concave down and any possible inflection points. So that's typically what I'm looking for, what I'm doing when I'm graphing something, is I'm looking for all that stuff. So let's start off with a relatively not terrible example. Let's look at the function f of x equal to x to the fourth minus 4x, which I want to graph. So I'm going to find all the things. I'm going to find my y-intercept. That's easy enough. I'm going to set x equal to 0. F of 0 is going to be 0 minus 0, which is 0. Great. X-intercept. I'm going to set the whole thing equal to 0. I feel like this picture quality could be a little bit better. Let's see if I can brighten this up a tiny bit. I don't want to go too bright because then it washes out, but I want to be bright enough so you can see it. So setting this equal to 0, I'm going to factor. I'm left with x cubed times x minus 4 equal to 0. So I either get x equal to 0 or x equal to positive 4. All right. This is a polynomial, so there are no asymptotes. And that's always true. Polynomials never have asymptotes. And then we're going to look for the first derivative stuff. So when I say first derivative stuff, what I really mean is find the critical points and then draw the number line for the first derivative using the critical points. So here's my derivative. It's going to be, let's see, 4x cubed minus 12x squared. And I'm going to set that equal to 0. I'll remind you that when you're finding critical points, you're really taking the derivative and setting it equal to 0 or undefined. But we know this expression is never undefined because there's no division by 0, there's no even roots, there's no logarithms. Let's factor this. I'm going to factor out a 4x squared. I'm left with an x minus 3. And so I either get x equal to 0 as a critical point or x equal to 3 as a critical point. And then we're going to put those on the number line. The number line for the first derivative. So put 0 and 3 here. Now I'm just going to test points. So I'm going to test something larger than 3, like 5. If I plug in 5 to the first derivative, I'm going to get a positive times a positive, which is positive. And then I'm going to test, well, you could either keep testing points or you could use the multiplicity. So you could either say 3 came from this factor has an odd multiplicity, so the sign is going to change. Or you could pick something like 1 and plug it in and see that it's a positive times a negative, which is going to be negative 4. And then I do the same thing here. You can either say 0 came from this factor with an even multiplicity, so the sign is going to stay the same. Or you can pick something like negative 1, plug it in, and see that 4 times negative 1 squared is positive, times negative 1 minus 3 is going to be negative. And then I think it's definitely worth your while to say, well, if it's negative, then the function is decreasing. The function is decreasing. And then if it's positive, the function is increasing. I will point out, Usually people don't ask you to say where it's increasing or decreasing. Like when you're graphing something, usually you don't have to state where it's increasing or decreasing, but we should still talk about what it would be here. So this function is definitely increasing on the interval from 3 to infinity. And unless your teacher is doing something strange, we always talk about intervals of increasing or decreasing being open intervals. Occasionally, some classes in the past have described it as being a closed interval, which is atypical. And your book definitely defines it to be an open interval. Now, where is this function decreasing? Well, it's decreasing here, and it's defined at the point between them. So we would say this function is decreasing on the entire interval from negative infinity to 3. Are there questions about that? We'll see graphically, when we graph this thing, I'll talk about why this is the case, and then we'll see another example where, excuse me, something different happens. Let's talk about the second derivative stuff. I should also point out, though, that once you've got the first derivative stuff, you really know a lot about the shape of the graph. We know this thing is going to go down, hit 0, hit the point 0, 0, right? Because that's one of our points. Keep going down to this minimum here at 3, comma whatever, and then get better. We probably should also write what the relative extreme is. So we have a relative, or local if you prefer. We have a relative minimum at x equal to 3. Because the function was decreasing to the left of 3 and increasing to the right of 3. Typically, when we graph things, we usually find the associated y value of that. So if I want to find f of 3, this is where it's really good to think about how you factored it. So f of 3, I could plug it into the original function and say it's 3 to the 4th minus 4 times 3 cubed. But it's a lot easier to plug it into the factored form. Say, oh, it's 3 cubed times 3 minus 4. That's much nicer to calculate. That's just going to be 27 times negative 1. Great. Now let's find the second derivative stuff. If you have the option, you can either take the derivative of 4x cubed minus 12x squared or the derivative of 4x squared times x minus 3. I don't want to use the product rule unless I really need to. I definitely don't need to use the product rule here. I'm going to use this version of the first derivative to take the second derivative. So I'm taking the derivative of this and get 12x squared minus 24x. And then I'm going to set that equal to 0. I'm going to factor, and then we get 12x times x minus 2 equal to 0. So my critical values for the second derivative are x equal to 0, x equal to 2. Put those on a sign chart for the second derivative. And let's see, if I pick something larger than 2, like 3, I get 12 times 3 times 1, which is positive. Pick something between 0 and 2, like 1, 12 times 1 times negative 1. And pick something less than 0, like negative 1, you get negative times the negative, which is positive. So this function is concave up, concave down, concave up. Which means we have 2 inflection points. We definitely have an inflection point at x equal to 0. We already know the y value there is 0. We also have an inflection point at x equal to 2. And the y value there is f of 2, which is, we'll get going back to the original function. If I plug in 2 to my function here, it's going to be 8 times negative 2, which is negative 16. And we get an inflection point wherever the concavity changes. I should say, we get an inflection point wherever the function is defined and the concavity changes. So definitely there, definitely there. And now we can draw. I mean, we could have drawn it probably a while ago, but let's draw it. So let's see, I'm putting it all together. So I'm going to draw my points, and I have the point 0, 0. And I also have the x-intercept 4, 0. And then what else did I have? I had a critical point at 3, comma, I should say not a critical point, a relative minimum at x equal to 3, y equal to negative 27. I'm not going to worry about trying to make the y scale look right. I'm just going to say, well, it's at 3. It's going to be down here somewhere. And then I also have my inflection point at 2, negative 16. So somewhere here, okay. And then what I'm going to do is I'm going to use the sign chart from my first derivative to help me graph this thing. Left of 0, it's going to be decreasing. Right of 0, it's going to be decreasing. And then at 3, it's going to be, after 3, it's going to be increasing. Now, I also know that at 0, it kind of flattens out, right? The derivative at 0 is 0. So I kind of have this thing where it's going to be like, okay, decreasing, 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 and then it kind of flattens out, and then it keeps decreasing again. And then we bottom out, and then we are increasing after that. I have an inflection point at 0. The function goes from being concave up to concave down. And then I have an inflection point at 2, negative 16. The function goes from concave down to concave up. Another way to think about where the concavity changes is where the first derivative, well, so here's something I think you all want to know about just as a quick aside here. When a function is concave up, and when I say concave up, I think of like a cup. So this function is concave up, like a cup, like that. And there are 3 things that are true when a function is concave up. I mean, there's more than 3 things, but like, okay. Thing 1, I'm just going to write that the function f of x is concave up. Well, what does that mean about the first derivative? Well, the first derivative, and I should say, right, whenever we're talking about the behavior of a function, we're almost always talking about from left to right. So if you say a function is increasing, we mean it's increasing from left to right. If it's decreasing, it's decreasing from left to right. Always left to right. So when I look at this function, when I look at the derivative of this function, from left to right, the derivative starts off being very negative or very positive. Right, it's super negative, right? Look at that very steep negative slope line. And then as we move to the right, it's still negative, but it's less negative. So the derivative has increased. And it's 0 here. It's slightly positive here. It's even more positive over here. So for this concave up function, the first derivative is increasing. Okay, I'm going to go back for just a second. And I would love people to chat if you want to chime in chat-wise. Otherwise, I'm just asking. You know what? I forgot your name. I know I should know your name. Tell me, remind me of your name. Ying? Okay. Just me and Ying here. So I feel like I don't want to ask for all the questions in the world, but I might. So let me ask you all and you. If something is increasing, don't even look at this. If something's increasing, what does that mean about its derivative? Well, so let me look like for this function over here. This function is increasing, and in this interval where it's increasing, what do we know is true about the derivative where the function is increasing? Right, the derivative is positive, and that's a true thing. If something's increasing, if some function's increasing, its derivative is positive. Okay, so now look back here. This function, f prime of x, is increasing. Its derivative is positive. So these 3 things are equivalent. When the function is concave up, that means the first derivative is increasing. That means the second derivative is positive. And we have a similar thing being true about if a function is concave down. So concave down, like a frown. When the function is concave down, well, it is concave down. The derivative is decreasing, right? It starts off being super positive, right? Very positive derivative, less positive, 0, slightly more positive, more positive. Sorry, I said that backwards. Very positive, less positive, 0, slightly negative, more negative. So the derivative is decreasing, and the second derivative is negative because the rate of change of the first derivative is negative. So I think it's worth noting this. So when we look back on our graph, right? Oh yeah, we see that from negative infinity to 0, the function is definitely concave up. Or right, my derivative is increasing because it's very negative, less negative, and then 0. And then from 0 to 2, the function is concave down. So the first derivative is decreasing. It's slightly negative, more negative, more negative. And right here at the inflection point, the first derivative is as negative as it can be. Right? We're decreasing for the first derivative, it's super negative, and then the first derivative starts increasing. So it's being less negative, 0, positive, positive. So an inflection point is often where the first derivative either reaches a maximum or a minimum. So this inflection point right here, the first derivative is the biggest it can be in this interval, it's 0. This inflection point right here, the first derivative is as negative as it can be. I don't know what it is, but it's something. You can plug it in and check, but I don't want to. So I know it's a little bit extra here. As far as graphing, I'm really looking at the first derivative sign chart to help me kind of see how the shape looks. And then I'm kind of looking at the second derivative sign chart to make sure the concavity matches up how it should. Questions about any of that before we do another example? I'll remind you all too, I know I've written it many times, but I know when someone writes something about the same contract to ignore what they've written. The chat is private, so if you do have questions that you feel like maybe you don't want anyone else to see, no one else is going to see your questions except for me. All right, well, let's move along to another example. And yeah, we should talk about that one. Okay, so we'll come back to that. Let's look at this example. So get f of x equal to x minus 3 x to the 2/3 power. All right. So graphing this thing, I'm going to follow the same path that I took before. I'm going to find all the same usual things. So let's find the intercepts. So y-intercept, set x equal to 0. You're going to get f of 0 equal to 0 minus 3 times 0 to the 2/3 power. 0 to the 2/3 power is definitely 0. X-intercept is going to be a little bit more work. So you have x minus 3 times x to the 2/3 equal to 0. Whenever you're trying to find x-intercepts, you usually want to factor the thing. And I can factor out an x to the 2/3 here. I can always factor out the smaller power of it, so the smallest power of x. So I've got x to the 2/3 times x to the 1/3 minus 3. Okay, so I'm either going to get x equal to 0. By the way, I already knew x equal to 0 was going to be an x-intercept because I already have that y equal to 0 was a y-intercept. So that means the origin is an intercept. So it's both an x and a y. And then from here, I'm going to get x to the 1/3 minus 3 equal to 0. So x to the 1/3 equals 3. So x has to equal 27. So those are my two x-intercepts. X equal to 0, x equal to 27. Asymptotes. Asymptotes. Vertical asymptote? Maybe. Probably not, though. Definitely not, actually. No. You can't have a vertical asymptote if the function isn't undefined anywhere. So this function has domain everything. Right, and to have a vertical asymptote, the function needs to be undefined. And then horizontal asymptote, probably not. If we look at the factored form, it's easier to see. F of x equal to x to the 2/3 times x to the 1/3 minus 3. You can see that as x gets very, very large, you're going to get a very large number times a very large number, which is going to be very large. And as x gets very negatively large, you're going to have a very positively large number. because a negative number, cube root is still negative, but then when you square it, it's positive, times a very negatively large number, because the cube root of a negative is negative. So what I'm thinking about here is, as x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, f of x goes to negative infinity. And to have a horizontal asymptote, when you go either out to infinity or negative infinity, the function has to get close to a particular number. We also probably could have seen this just by looking at the first derivative stuff. So I usually kind of, if the horizontal asymptote isn't really, really obvious, whether or not there is one, I usually skip this part and just be like, okay, I'm going to come back to this after I've looked at the first and second derivative, because it's usually more clear after that. All right, let's look at the first derivative. So the first derivative is going to be 1 minus 3 times 2/3 x to the negative 1/3. Oh, sorry, thank you, appreciate it. It's all on you, right? If you want to say something or you guys want to say something. And we're going to set that equal to 0. Yeesh. Okay, slash undefined, right? It can be 0 or it can be undefined. So simplifying a tiny bit, I've got 1 minus 2 times x to the negative 1/3 equal to 0 slash undefined. So I want to point out right now, 0 makes this undefined. If you plug in 0, 0 to a negative power means you're essentially dividing by 0. So right away, x equals 0 makes the derivative undefined. Now, it probably would have been easier to see that if I just rewritten it, but I want you to kind of get used to, just be aware, right? If you've got something to a negative power, it means it can't actually be 0. People often make the mistake of saying 0 to any power is 0, whereas the correct statement is 0 to any positive power is still 0. 0 to a negative power is undefined, and 0 to the 0th power is a weird indeterminate form, which we talk about later with L'Hopital's rule. Well, let's find where it's actually equal to 0. So 1 minus, I'm going to rewrite this as 2 over x to the 1/3 equals 0. And then 1 equals 2 over x to the 1/3. And then x to the 1/3 equals 2. And then x equals 2 cubed, which is 8. Now, 0 is still a critical value because it makes the function and the derivative undefined. And I should be extra specific here. It's a real critical value, right? It's a place where the derivative is undefined and the original function is defined, right? It's not like an example where you've got like a vertical asymptote and the derivative is undefined there because the original function was also undefined. We'll see when we see the next example. I'll refer back to the, oh yeah, that's kind of what I'm talking about. But here, these are both are critical values. So let's look at the sign chart for the first derivative. So I'm plugging in 0 and 8. Do make sure you don't make the silly mistake of writing the orders in the wrong order or writing the numbers in the wrong order. I was doing a problem earlier with someone and accidentally wrote like 0, -4 in the wrong spot. So just be careful. It really helps to get things in the right space. Testing points. So I did myself kind of a disservice here. I probably could have, in fact, I'm curious about. All right, sure. So yeah, I want to plug in points to the first derivative, and I should probably look at this. That is my first derivative still. If I plug in something bigger than 8, what's a number bigger than 8 that's easy to plug in? Well, 9 kind of. I don't know what 9 to the 1/3 power is. (27). You plug in 27, the cube root of 27 is 3, and 1 minus 2/3 is going to be positive. Now, really, if you said 9 is okay. You have to realize that the cube root of 9 is bigger than 2, and so 2 over that is smaller than 1, and 1 minus that is going to be positive. Easy number between 0 and 8 is 1. 2 over 1 is 2, and 1 minus 2 is negative. And then a number less than 0, like -1. -1 to the 1/3 power is still -1. So 2 over -1 is -2, and 1 minus -2 is going to be +3. Or positive. Yeah, it might have been better if we had simplified this in a different way and gotten a common denominator. If we had instead said this was x to the 1/3 minus 2 all over x to the 1/3. That might be better. It might not be better. It still feels like we'd have to be careful checking our work here. In any event, we know that the function is increasing and then decreasing and then increasing. So we have a relative maximum at x equal to 0. We have a relative minimum at x equal to 8. Now, I'm also going to mention, we know that when x is 0, the derivative is undefined. So this relative maximum is going to be pointy. It's going to probably be it's going to be like a cusp. This is where, so especially in this case, when you have something weird like this, it really does kind of make sense to think about the concavity before you try and graph the thing. So let's talk about the concavity. So let's look at my second derivative here. So my second derivative is going to be, so here, oh, you guys can't see it anymore. There's my nice first derivative. Second derivative is going to be 0 plus 2/3 x to the -4/3. Well, that's not too bad. I'm going to write that as 2 over 3 times x to the 4/3. And what's my only critical value here? Well, there's only one thing that makes this either 0 or undefined, and it's 0, and it makes it undefined. Right? If you plug in 0 here, that's going to be an undefined thing. So for my second derivative, there is 0, and if I pick something larger than 0, like 1, 2 over 3 times 1 to any power is 2/3, positive. And if we pick -1, -1 to the 4/3 power is +1. Because it's the cube root, which is -1, but the -1 to the 4th is positive. So it's also positive here. So our function is concave up on the left and concave up on the right. All right, so trying to graph this thing. We have an intercept at 27. Sorry, now I'm kind of pointing at things you can't see. We have intercepts at 0 and 27. And we know we have a relative maximum at 0. So it's going to be increasing, decreasing. And then we have a relative minimum at 8. Oh, and we should find the y value for 8 because it's going to help us. So for a relative minimum at x equals 8, f of 8 is going to be 8 minus 3 times 8 to the 2/3 power. And if we simplify that, that's going to be 8 minus 3 times 8 to the 2/3 is 4. So we get 8 minus 12, which is -4. So about there-ish. You don't have to be very, what am I trying to say here? Your scales on each axis don't have to be the same. My x-axis scale and my y-axis scale are typically wildly different to make it easier to graph. So I know in here it's going to be concave up. So I'm going to do something like this. And over here, I'm also concave up. So maybe I'm something like this. But I also know, right, from -3 to 0, I have to be increasing. From 0 to 8, I have to be decreasing. From 8 to infinity, I have to be increasing. So I just want to point out, right, even though, so it's concave up over here, we can't like turn around like that. And it might be tempting to want to be like that, but it's not, because if I did, this, pretending like it was that, right, then it would be decreasing here, and I can't have that because everywhere to the left of 0, it has to be increasing. So we don't have this. It just keeps going that way. Yeah. And then just to reemphasize, right, we have this cusp at 0, 0 because the first derivative is undefined there. But the function is continuous, right? Here's an example of a continuous function that is definitely not differentiable everywhere. Specifically not differentiable at 0, 0. Any questions from the Zoom land? Any questions from you? Oops, sorry, I was just at the one. Oh, let me send that to everybody, not just to one student. Here's the attendance form again. Please do fill it out when you have a second. Okay, let's look at another graphing example. And then we're going to make some comparisons. So we're going to make our lives a little bit easier for this next example. I'm going to give us all the derivatives to start off with. So we're going to graph this function. F of x equal to x squared minus 8 over x minus 2 quantity squared. And instead of actually finding the derivatives, because they're kind of a giant pain, I'm going to tell you that the first derivative is 16 minus 4x all over x minus 2 cubed. And the second derivative is going to be 8x minus 40 over x minus 2 to the fourth. This actually brings up an important thing that I've noticed over the years, which is the following. So I actually just want to show you guys something. Even though I said we've already been given the derivatives, but let's say we wanted to actually find f prime. So when you find f prime, I'm going to close that door. There's always a mass exodus and it quiets down. Let me just. So if I was going to find the first derivative, it would be the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2 times x minus 2, all over the denominator squared, which is x minus 2 to the fourth. You notice that when we simplify this, we end up with an x minus 2 cubed on the bottom. I mean, like, so if you did all of this, you would eventually get to that. And what happens every time when you differentiate some quotient is the power in the denominator after you have simplified everything gets to be 1 larger. Right? I know we squared it, right? You've got this 4, but then what's going to happen is you're going to factor out an x minus 2 from the top and cancel that x minus 2 with 1 into x minus 2's in the bottom. The same thing is true when you find the second derivative. If I take my first derivative and differentiate it, it's going to be the bottom times the derivative of the top, which is 3 times x minus 2 squared, minus the top, sorry, bottom, I did that backwards. So that's not right, right? It should be the bottom times the derivative of the top, not the top times the bottom, sorry. It's the bottom times the derivative of the top, which is -4, minus the top times the derivative of the bottom, which is 3 times x minus 2 squared, all over the bottom squared, which is x minus 2 to the 6th. And what's going to happen here is you're going to factor out an x minus 2 squared from the top and cancel 2 of the x minus 2's and end up with an x minus 2 to the 4th. So every time you differentiate a quotient, if you do the simplification, the denominator ends up being just 1 higher power than it was before. It's a useful piece of information to know that that's what should happen when you simplify things. Anyway, but we're going to pretend like we did all the work, we simplified it, and it all worked out nicely, and we got these derivatives. So let's go ahead and find all the stuff. So I'm going to find my y-intercept. It's going to be f of 0, which is going to be -8 over 0 minus 2 squared is going to be +4. My x-intercept, I'm going to set the whole thing equal to 0, but really I'm just setting the numerator equal to 0. So x squared minus 8 equals 0. We're going to get x equal to plus or minus the square root of 8. Or if you prefer, x equal to plus or minus 2 root 2. Great. Let's find the asymptotes. So I definitely have a vertical asymptote at x equal to 2. I definitely have a horizontal asymptote. Oh, what's my horizontal asymptote? Well, the degree on top is 2. If you multiply at the bottom, the degree on top is also 2. Or I'm sorry, on the bottom is also 2. So my horizontal asymptote is y equal to 1 over 1. The leading coefficient on top divided by the leading coefficient on the bottom. All right. At this point, you might even start plotting things. So I have a horizontal asymptote of y equal to 1. I have a vertical asymptote of x equal to 2. And I have intercepts at positive root 8, which is a little smaller than 9, or sorry, it's smaller than the square root of 9, which is 3. And negative root 8, which is going to be not quite as negative as negative 3. And then I also have a y-intercept of negative 2. So there's what I've got so far. Let's find the first derivative stuff. So again, my first derivative is 16 minus 4x over x minus 2 cubed. So critical points. Set this equal to 0 / undefined. Setting it equal to 0, you get 16 minus 4x equal to 0. You get x equal to 4. What makes this undefined? Well, x equal to 2. Now, something to point out here. X equal to 4 is a true critical value. It's a place that makes the derivative 0 or undefined, and it's in the domain of the original function, right? There's my original function up there, x squared minus 8 over x minus 2 squared. On the other hand, x equal to 2, if someone gave you this function and asked you what are the critical values, the only answer would be x equal to 4. X equal to 2 is not a true critical value. Now, I should be careful here. Your professor might have defined things slightly differently. Some people do actually define the critical values to be places where the derivative is 0 or undefined, even if it's not in the domain of the original function. But the usual typical definition of a critical value is it has to be a place where the derivative is 0 or undefined, and it has to be in the domain of the original function. So this is not a true critical value, but it's still important. It's still a place where the sign of the derivative might change, so we definitely need to include it on our number line for the first derivative. So when I draw my first derivative number line here, I'm going to put 2 and 4 because I want to know where the function's increasing or decreasing, even if the point in between those two things is not actually going to be a relative max or relative min. So picking something larger than 4, like 5, I see the numerator is negative, I see the denominator is positive, the overall sign is negative for the first derivative. Picking something between 2 and 4, like 3, numerator is positive, denominator is positive, the whole thing's positive. Picking something less than 2, like 1, or even 0 is probably a better choice. Numerator is positive, denominator is negative. So my function is decreasing, increasing, decreasing. And now here's where I could ask you a question meant to be a trick. Well, first question is not a trick. Where do I have a relative maximum? Right. And we'll find the y value in a second. Okay, now here's the trick question. Where is there a relative minimum? There isn't one because the function is undefined at 2. So no relative minimum. Which is why it's a good idea, I think, when you're doing this kind of problem, to draw out what you have before you kind of like draw out your asymptotes before you start doing your first derivative stuff. So that like when you see 2, you're like, oh, there's a maximum there. And then you go back and you're like, oh, wait, I can't plug in 2. I've got a vertical asymptote. But people, right, if you were just like, if someone asked you this question and said, don't graph it, just find the relative extrema, it'd be really easy to make the mistake of saying, oh, I have a relative minimum of 2. I don't, right? The function is undefined at 2. So now we know the behavior, like we can probably draw the graph at this point, because I know from 0 to 2, it's going to be decreasing. It's going to be decreasing, 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 decreasing. And then from 2 to 4, it's going to be increasing. And at 1, 2, 3, 4, I'm going to hit a relative maximum. Just probably find out what f of 4 is. It's going to be, let's see, f of 4 is going to be 16 minus 8 over 2 squared. So that's 8 over 4, which is 2. And then after that, it's going to be decreasing. So let's do something like this. And then it's going to be increasing. Top out. And then. Okay. Now, the way I've drawn this, it looks like there has to be an inflection point somewhere over here, right? Because you can't just, if you keep decreasing, you can't be concave down the whole time. You're going to have to be changing to being concave up. There's something else I wanted to point out. Oh, I will also mention, it's not that important, but I want to just emphasize to everybody, we can definitely cross a horizontal asymptote. Sometimes it happens. What's CV? A CV is a critical value, meaning a place where the derivative is either undefined or equal to 0. So when you plug in x equal to 4, this derivative is going to end up equaling 0. And some people say critical value, some people say critical point, same idea. Sometimes people differentiate between them. So if I was saying critical value, I usually just mean the x value. Or if I say critical point, I kind of mean the xy coordinate. So let's talk about the second derivative stuff for just a second. My second derivative was 8x minus 40 over x minus 2 to the 4th. And I would say that the critical values here, so the critical values are going to be x equal to 5. Because if you plug in 5 for x, you get 0 in the numerator. And although it's not a real one, I'm still going to include x equal to 2, because it's a place where something might change. So looking at the number line for the second derivative, I have 2 and 5. Plugging in something larger than 5, like 6, the numerator is positive. The denominator is always positive for this particular function. So it's going to be positive. Picking something between 2 and 5, like 3, negative on top, positive on the bottom. And putting something like 0, negative on top, positive on the bottom. So this function is, I said negative on top and positive on the bottom, and I wrote positive. That should give me negative. Apologies. The function is concave down, concave up. So we definitely have an inflection point. Fade. Inflection point at x equal to 5 with a y value of f of 5, which is going to be, I plug in 5 back to the original function, which is up there. I'm going to get 25 minus 8, which is 17, over 5 minus 2 squared, which is 9. And I don't know exactly what 17/9 is, but I do know it has to be a value that's a little bit lower than 2. And it is, because 17/9 is just a little bit less than 18/9. So there's my function. Yeah. So let's do maybe 1 or 2 more graphs, and then we will switch gears and talk about optimization. Yeah, I'll take that one. That one feels sure. Yeah, no, that's good. I'm just trying. I feel like there was something I wanted to say before. I just want to make sure. So yeah. Yeah, we'll get back. We'll come back to that. Okay. Yeah, I think one more graphing example, then I'll use the restroom, and then we'll come back and we'll talk about optimization. So let's look at this example. Let's graph f of x equal to x squared over x minus 3. And we're going to give ourselves the derivatives again. The first derivative is x squared minus 6x, or x times x minus 6, all over x minus 3 squared. This is we're giving, oh, why is 2 not a, sure, fair question. Let me write out the second derivative, then I'll go back to that. Second derivative is going to be 18 over x minus 3 cubed. Okay. There's a question, why is 2 not a true critical value for the first derivative? So if you look at the definition of a critical value, at least the standard definition is that, yeah. So we talk about critical values. So the definition of a critical value. So C is a critical value of f of x if C is in the domain of f and either f prime of C equals 0 or f prime of C does not exist. So the issue here isn't, right, if you plug in 2, f prime of 2 certainly doesn't exist, but 2 is not in the domain of the original function. And that's what's keeping it from being a true critical value. However, it is still really important, right? If you didn't have 2 here, you would miss the fact that the derivative goes from negative to positive, and it would be harder to see what the behavior of the graph looked like if you didn't keep 2 on there. So even though 2 isn't a true critical value, it is still very important that we include it on our number line for the first derivative. Hopefully that clarifies things. No, not necessarily. Sorry, I'm answering a question that nobody else has seen. So the question is, doesn't a critical value not existing mean it's not in the domain of the original function? That's not the case. So if we look back at, I think the second question we did, yeah, if we look back at this one, f of x equal to x to minus 3x to the 2/3, that function is defined everywhere, right? Any value of x you plug in, you get a y value out. Specifically, 0 is certainly in the domain of this function. F of 0 is 0. But when we took the first derivative was 1 minus 2 over x to the 1/3. And if you plug in 0 there, the first derivative is undefined. So when that happens, it's a true critical value, right? The derivative is undefined, and 0 definitely is in the domain of the function. And when that happens, when you have a function where the derivative is defined, or sorry, undefined, but still in the domain of the original function, you end up with a cusp, or a pointy point, as I like to call it. So this function definitely is defined as 0. F of 0 is 0, but the derivative does not exist because the derivative is super, it's actually, in this case, the derivative is, well, on one side, the derivative is approaching positive infinity because we have very, very steep slopes that are positive. On the other side, the derivative is approaching negative infinity because you have very, very steep slopes that are negative. But even if they're both approaching the same sort of infinity, it would still not exist because it would be a vertical tangent, which has an undefined derivative. Good, I'm glad you see. Okay. Sorry, I got that backwards. Okay. Look at this next example, which is going to be similar. Let's see. So again, usual stuff. We're going to do this one kind of quick. So y-intercept, f of 0 is looking to be 0. X-intercepts, set the whole thing equal to 0. Specifically, set x squared equal to 0. You're going to get x equal to 0. So our only intercept is the origin. Vertical asymptote, x equal to 3. Horizontal asymptote, there isn't any, and that's always the case in a rational function when the degree on top is larger than the degree on the bottom. But since the degree on top is exactly 1 larger than the degree on the bottom, we do have a slant asymptote, which you find by doing polynomial division. So x minus 3 into x squared plus 0x plus 0. X times x gives me x squared. X times x is x squared. X times negative 3 is minus 3x. Subtract. x squared minus x squared is 0. 0x minus negative 3x is positive 3x. X times 3 gives you 3x. And you can stop right there. So stop there. You don't have to do anything else. Your slant asymptote is y equal to x plus 3. There's absolutely no need to finish this polynomial division. You certainly could if you wanted to. So I'm going to finish it just so you can see what's happening. If you finish it, you get 3 times x minus 3, which is 3x minus 9. Subtract 0, and 0 minus 9 is 9. So what we're really getting here is that this function, x squared over x minus 3, is equal to x plus 3, the quotient, plus the remainder divided by the divisor. And what's happening is, so usually when you find a horizontal asymptote, you ask the question, what happens to the function as x goes to infinity? And like in the previous example, oh, come on, previous example. Oh my gosh, maybe someday. So in the previous example, our function, I feel like I keep getting way on the screen here. Our function was x squared minus 8 over x squared minus 4x plus 4. And this gets closer and closer to 1 as x goes to infinity. Because the only thing that really matters is the x squared and the x squared, the biggest thing on the top and the bottom. And they're the same as each other. So the limit's going to be 1. You can also use L'Hopital's rule, or you can do the thing where you divide from the x squared. But the point is, we're asking the question, when you're asking about the horizontal asymptote, what happens to the function as x gets really, really big? Or really, really negatively big? Well, the same thing is true here. Not here, right here. What happens to this as x gets really, really big? Well, as x gets really, really big, this part is going to be very, very small. So the limit as x goes to infinity of this expression is going to be just the x plus 3 part. Because this part here is going to get very, very small. So what we're saying is, as x gets really, really big, this function gets very, very close to the line y equals x plus 3. All right. So now let's talk about all the derivative stuff. So we're going to find critical values. We're going to set the first derivative, x times x minus 6 over x minus 3 squared equal to 0, slash undefined. So we're going to get x equal to 0, x equal to 6, and x equal to 3 is a pretend critical value or a pseudo critical value. You don't even need to really write that. You just, I like to remind myself that 3 is not a real critical value. SA means slant asymptote. So it's not a horizontal asymptote. It's a line y equals x plus 3. It's going to be what the function gets closer and closer to as x moves out in either direction. We'll graph in just a second, we can see. First derivative number line, I'm going to put all of my real or pseudo critical values on there. So looking at the first derivative, I'm going to see, let's see, so if it's bigger than, if x is bigger than 6, I'm going to positive, positive, positive. And then I'm going to change signs at 6. My sign is going to stay the same at 3, and my sign is going to change at 0. So the function is increasing, decreasing, decreasing, increasing. I have a relative maximum at 0. And we already know the y value there is 0. We have a relative minimum at x equal to 6. And the y value there would be f of 6, which is 6 squared over 6 minus 3, which is 36 over 3, which is 12. And then we don't have any, well, I mean, so we want to talk about the second derivative. That doesn't ever equal 0, but it is undefined when x is equal to 3. Again, not a real critical value, but the concavity does change on either side of 3. So if you do something larger than 3, like 4, the second derivative is going to be positive. If something less than 3, like 0, the second derivative is going to be negative. So the function is concave down over here, concave up over here. Which means we have an inflection point at 3, right? No, not right. Right? Because at 3, we have a vertical asymptote. So no inflection point at 3. Because the function itself is undefined at 3. So be careful there, right? You should always be thinking about, is that point where the function is undefined? Oh, then it can't be anything. It can't be an inflection point. It can't be a critical value, or it can't be a relative extrema. It can only be a vertical asymptote. So let's graph the thing. I'm just going to put everything on my graph. So I have 0.00. I have a vertical asymptote at 3. And I have a slant asymptote at y equals x plus 3. So y equals x plus 3 would have a y-intercept of 3 and an x-intercept of -3. I'm going to draw it dashed just like I would draw any asymptote. So there's my slant asymptote, y equals x plus 3. And then I think that's all. Oh, then I've got the critical point 6, 12, which I will label once I've drawn the thing, and also 0, 0. So I'm just going to say, well, if I look back here, sorry, one sec. My function is increasing before I get to 0, 0, decreasing after. Just to look like this. And then after 3, it's still decreasing. And then at 6, it's going to start increasing. So 4, 5, 6. Hit that minimum. And then increase afterwards. Sorry, I can't sell that. One last thing about this function. So I want to point out that if someone asked you to write down the intervals where this was increasing or decreasing, here's what we would see. So looking back at my first derivative sign chart for just 1 second, this function is definitely increasing. Sorry, can you guys see that? Yeah, you can see it. It's increasing on the interval from -3 to 0, union 6 to infinity. And it's decreasing on the interval. Now, it's not the interval from 0 to 6, because you can't include 3 because the function is undefined at 3. So the interval it's decreasing on is 0 to 3, union 3 to 6. And that's a little different than the first function we looked at, because the first function we looked at was defined, right? So, right, this function, on the other hand, this one here, was decreasing from -3 to 0 and 0 to 2, sorry, 0 to 3. But we got to write that as one interval because it wasn't undefined at the place where you had a critical point. So if it's defined there, you can include it and say it's, decreasing from -3 to 3. But if, right, even though 0 was a critical point, apologies, right? So there's the sign chart there. We included 0, it was decreasing, but it's defined at 0. Whereas the one we just talked about, you can't include the 3 here because although it's decreasing, the function is undefined at 3. It's not a huge deal, but just something to be aware of. Again, in actuality, we're usually not being, I don't know, that's not true. Sometimes you're being asked for something's increasing or decreasing, but like it's not often the thing we're being asked about. So I don't want to focus too much on it. Let's take a quick break so I can pee, and you all can also pee if you need to, or get some water. I'm also get some water. Yeah, so I will go do that. I'm going to pause the recording. but remind me. Great, we're back. So optimization to me, process-wise, feels similar-ish to related rates. They're not the same, right? They're very different, but it's still kind of like, it's a bunch of steps where you have to kind of do it's the process for optimization always feels like you're doing this and then this and then this and then this. So it's very much like related rates in that we're going to do the same kind of thing each time we solve an optimization problem, even though the actual problem might be very different. So let's look at this example. Sure. You have 108 square inches of material to make an open-topped rectangular box. With a square base. What dimensions of this box will give us the maximum volume? Because we want to hold all the stuff. So instead of trying to draw a picture the one that is good, I'll just point out there are lots of different shaped boxes that meet these conditions, right? You could draw, we'll come back to this in just 1 second, but you could draw a box that looked like this, where the base was 2 inches by 2 inches and the height was 13 inches. The volume of that box would be 2 times 2 times 13, which is 52 cubic inches. And it would definitely have the right amount of surface area because the base would be 4 square inches and each side would be 26, and 26 times 4 is 104, plus 4 is 108. Or you could have this really, really short open box where the height of it is 1 inch and the bases are each 8.5 inches long, approximately. And the volume there is going to be 72 cubic inches, and it does have the same amount of surface area. It's got right, and right, this 8.5 really is like the square root of some number. I think it's the square root of 100 and something, I don't know. But the idea here is, right, there's a lot of different boxes that have that much surface area. We want the one that has the most volume. So what are we going to do? Well, we're going to first draw a picture, which is also the first step when we do related rates. So I'm going to draw my box, and I don't actually know the dimensions. I'm going to label the unknown dimensions with variables. There's my box. I didn't draw it very well, but you know, it's a box. And so I don't know what anything is, so I'm going to label some side stuff. So I'm going to call this side length X. And then here's the important thing. Since the base is square, we also have to call this side X. You never want to use more variables than you absolutely have to. I'm going to call that side X, that side X. But this side here, there's nothing telling me that the height is the same as the base. So I'm going to have to call that something different. Let's call it Y. But really, you never want to, like, you don't want to call this X, Y, and Z. You want to use X, X, and Y because we know that the base is square. So what are we trying to maximize? Or more generally, optimize? Well, in this case, they said we want to build the box with the most volume. So we're trying to maximize the volume. And the equation for volume is going to be, and most of these are usually geometric equations. The equation for volume of a box is just X times Y. Now be careful. The thing we're trying to optimize, we don't know what the maximum volume is. This shouldn't be being set equal to 108. I know there's a number that we're going to use, but the thing you want to maximize, you almost never know what it's actually equal to. It's just some function that you're trying to make as big as possible. The other thing we have, though, is the constraint. But the constraint is how much material we have to work with in this particular example. So we have 108 square inches of material. So we want to set the surface area equal to 108 square inches. So the surface area, well, the equation for the surface area is just all the area. So it's nice when it's a box because it's literally just add up all those squares and rectangles and see what you get. So my surface area, well, the bottom area is x squared. And then each side is going to be x times y. This front side is x times y, this right side is x times y, this left side is x times y, this back side is x times y. So I have 4 of those. And we know that the surface area, well, it could be less than 108, but we want to make it as voluminous as possible. So we're going to set it equal to 108. And it's almost always the case that if they say you can use up to this much material or up to this much, whatever, you should use all of it to get the most thing you're trying to get. So that's my constraint. And then typically what we do is we isolate a variable in the constraint. Most of the time, it should be relatively obvious which one to choose. Or in your homework, they might literally tell you, like, so like if I was doing this, if this was in like a web work problem, they might say, write the equation for the volume in terms of just the variable x. Meaning you have to take your constraint, solve for y in terms of x so that you can plug in y in terms of x back into the thing. So whatever they're telling you to write your function in terms of, you want to solve the constraint equation for the other variable. Also here, I definitely think it should look relatively, I feel like it's relatively obvious that y is the easier thing to solve for. Right? Solving for x here would require the quadratic formula. Solving for y here requires some subtracting and dividing. So definitely try to solve for the thing that's easier to solve for. I'm gonna have 4xy equal to 108 minus x squared. And then I'm gonna divide everything by 4x. So that y equals, how do I want to do this? That's fine. 108 minus x squared divided by 4x. And then we're going to plug that back into the original thing we want to maximize. So we're going to plug that in. And we get that the volume is equal to x squared times y. I'm going to close that there. I don't think anyone else is. Okay. So now we want to simplify this. It's going to be, well, I can cancel an x here and an x there. So I really got x times 108 minus x squared all over 4. And if I was going to simplify this in a way that's going to be easy to deal with in a minute, I'm going to rewrite this as volume equal to 1/4 times 108x minus x cubed. That seems like the easiest way to do what I'm going to do next, which is I'm going to take the derivative. And if we're trying to optimize something, trying to maximize something, trying to find where it's the biggest, we're trying to find where we have a critical point. That's how we find, that's normally how we maximize or minimize things. We find where the derivative is 0. So here's my volume as a function of x. And now we're going to differentiate that. Because really we're trying to find the critical values. So my derivative is going to be 1/4 times 108 minus 3x squared. I'm going to set that equal to 0. There's a number of ways you could do this. I suppose I'm going to be very specific here. So I'm going to factor out a 3 from here and say I have 3/4 times 108 divided by 3 is 36. So I could say 3/4 times 6 minus x times 6 plus x equals 0. So what are my critical values? What's one of them? And 0 actually isn't a critical value here. So if we plug in 0 for x, we don't get the derivative equal to 0. Right. Positive 6 is definitely a critical value. And I want to talk about negative 6. Negative 6, I mean, technically for this function is a critical value. But if we look back at the original kind of setup, right, the original setup, x is the side length of this box. So it doesn't make sense for x to be a negative number. So when you're dealing with optimization specifically, you have to think about what's constraining, what kind of physical limitations you have. You might even say here that x definitely has to be greater than or equal to 0. Even equal to 0 seems a little bit weird, right? You wouldn't make a box where one of the edges was 0 long. That's not much of a box, really. Okay, so now here's where things get a little bit interesting. And I feel like, yeah. So what I'm struggling with here is, on your homework, you probably never have to check this, because most of your homework assignments, write the answer in web work and no one's looking to see if you showed any work. But what I want to mention is x equal to 6 might not be where this function is maximal, right? A critical value is a place where you might have a maximum, you might have a minimum, or you might have neither. So what I'm really trying to say is, usually, especially like on a test, you might be asked to check to see if it actually is giving you a maximum. So we're going to use the first derivative test. So we're going to check, does x equal to 6 actually maximize the volume? We're going to do this the same way we'd always do it. We're going to draw the number line, but we're going to be a little bit careful because we actually don't want anything, right? Smaller than 0 is garbage. So 0 is kind of the end of our domain. And we're going to put our one critical point, 6. And we're going to ask, what's the derivative of volume doing? Well, here's my derivative of volume. If I pick something larger than 6, like 10, well, I could plug it in here, and it's not too hard to see that it's negative. If you plug in 10 squared is 100, 300, 108 minus 300 is negative. But it's much easier if you actually plug it in here. If you plug in 10 here, 6 minus 10 is negative, 6 plus 10 is positive. Oh yeah, it's a negative number. If there's something between 0 and 6, like 1, 6 minus 1 is positive, 6 plus 1 is positive. Oh yeah, the whole thing is positive. So the function definitely is increasing to the left of 6, decreasing to the right of 6. So we definitely do have a maximum. So yes, x equals 6 maximizes the volume. We're still not done, because the question at the beginning said, what dimensions will give us a maximum volume? We found the x dimension, we still need to find the y dimension. Luckily, if you're asked to find the dimensions, usually it's pretty easy once you found one of them. We know x equals 6 inches is one dimension. And then if you look back, when you isolated one variable in the constraint, we already know what y is going to equal. There's our equation for y right there. Y is going to equal 108 minus 6 squared over 4 times 6, which is 108 minus 36 of 72 divided by 24, which is going to be 3. So y is going to be 3 inches. Oh, sorry, yeah. So the box with that much surface area that has the maximum volume looks like this. Should say the box with the square base that has the maximum volume is 6 inches by 6 inches by 3 inches. So that's our usual process for optimizing something like this. And it's quite a few steps, right? We draw a picture if it makes sense to. We write the thing we want to optimize. We find the constraint. We isolate the variable in the constraint. We plug that in to the thing we want to optimize. We differentiate until it's equal to 0 to find critical values. we check to make sure that it actually is giving us a maximum or minimum, depending on what we want. And then finally, we go back and find the other dimension if we're being asked to. The story my Calc 1 teacher told me when I was a student at UC Davis many years ago is that one time in the Air Force, someone was building a plane and they were trying to maximize the wingspan according to some function, and they took the derivative and set it equal to 0, found the critical values, and didn't check that it was actually maximum, and the Air Force built a plane with tiny little wings. I don't think that's actually true, but it drives home the point that we actually do need to check to see if something's a maximum or minimum, because it could lead to making mistakes. I will also point out that usually no one's going to ask you to find something, to maximize something and have there not be an answer. Right? If I say find the maximum of this function, I'm not going to phrase it in a way that doesn't leave you out. So they might phrase it as find where this function has a maximum or state that it does not have a maximum. But usually they're just saying find where this function is maximized or find where this function is minimized. So let's look at another example. What is the largest cylindrical can that can be made using 24 pi square inches of material? So if you're talking about a three-dimensional shape, and they say they want it to be as large as possible, they mean they want it to contain as much volume as possible. Right? So typically when we talk about something being large or small, we mean large in its largest dimension. Right? If I said, what's the biggest the square can be, I would mean, what's the square that has the most area? If I'm saying what's the biggest the cylinder can be, I mean, what's the cylinder with the most volume? And when we say using 24 pi square inches of material, when they talk about using some amount of material, that almost always means that's the surface area. Also, it's inches squared, right? It's not going to make sense if it's something other than the area. So pay attention to the dimensions or the units in your dimensions, because it does help you kind of figure out what's going on. So what we're really trying to do here is we're trying to maximize the volume of the cylinder with surface area equal to 24 pi square inches. That's what we're really actually doing. So it's good to kind of break down what's written and try and interpret it like, oh, what's the thing that they're really getting us to do? So I'm going to draw a picture again. Here's my cylinder. Now, I'll point out, this question is actually asking what's the largest cylindrical can, meaning what's the most amount of volume. It's not actually asking us to find the dimensions. We're still going to find them because it's usually the easiest way to do it. But just pay attention to what you're being asked for. So the radius is there, the height is there, and I want to maximize the volume, which is the base area times the height. Okay. My constraint is how much material or surface area I have to work with. So the constraint is given by the surface area. And for a cylinder, it's always kind of funky. So for a cylinder, and this is a closed top cylinder, right? I've asked questions before in classes like design a cup, a cylinder shaped cup, with the implication being that it's open at the top because you wouldn't have a cup where the top was also closed. But this one's definitely, it's like a Coke can, right? You've got a enclosure on the top and the bottom. So our surface area is going to be, well, the top area plus the bottom area, which is pi r squared twice. And then you have the around part, which if you think about, I always think about it like as a roll of paper towels. So if I took a roll of paper towels and had a paper towel that went all the way around, and I took it off the roll and then rolled it, what kind of shape would I have? Anybody? Yeah, it'd be a rectangle. And the area of that rectangle would be, well, the height is still the height, and the length is how far around we went, which is the circumference of the cylinder. which is 2 pi times the radius. So the area of this rectangular paper towel is 2 pi RH. And that's going to be equal to our 24 pi square inches. So there's our constraint. So what's going to be easier to solve for? The radius, which is occurring twice, or the height, which is occurring once? Definitely the height. There are rare instances where it makes more sense to solve for the more complicated thing. We might get to one of those examples. We probably actually won't, but next class I'll show you one of those where you have like pi r squared equal to something, and it actually makes more sense to solve for r squared. But 9 times out of 10, it usually makes more sense to solve for the thing that's simpler. So solving for h, we're going to have 2 pi rh equal to 24 pi minus 2 pi r squared. Let's divide everything by 2 pi, right? We don't need that constant. We've got RH equal to 12 minus r squared. And then dividing everything by r, h is going to be 12 over r minus r. Great, let's plug that back in. So now we're going to try and maximize volume equal to pi times r squared times 12 over r minus r. I don't need to distribute the pi, but because it's just a constant, it's not going to affect anything really. But I do need to distribute the r squared. Well, I mean, I don't need to, but I think it's easier to distribute the r squared. Like you could take the derivative of this as is. I would rather not use the product rule, but I don't have to. So I'm going to rewrite this as pi times r squared times 12 over r is 12 times r. And r squared times r is r cubed. And I haven't left myself really a lot of room up here, so if I will do here, critical values. So I'm going to take the derivative of this, and it's really v prime, or you can write it as v prime of r if you want. It's going to be pi times 12 minus 3r squared. Set that equal to 0, and we should be able to see what the possible answers are here. Possible answers are r could be 2 or r could be -2. Now, of course, we know that -2 for the radius doesn't make a lot of sense. So our answer here is that r is equal to 2 inches. Does that give us a maximum volume? We need to check. So going back to my derivative, plugging in 2, I'm saying 2 is my critical value. Picking something larger than 2, like 7, 12 minus 3 times 7 squared is definitely negative. Now, here's where you have to be careful. If you only think about 2 here and you say you can go as far left as possible, you might pick something too far left to plug in. For example, if I plugged in -3, I would get 12 minus 3 times 9, which is 12 minus 27, which is negative. Right? That's not going to be right. So we have to remember that really we are limited to the natural domain of this, which is that you can't go any further left than 0. So I'm going to plug in r equal to 1. Plug in 1, 12 minus 3 is 9, which is positive. So this function is increasing before 2, decreasing after 2. So r equals 2 inches does in fact give us a maximum. There's a question there. How do you get rid of, oh, they said never mind. All right. So now to answer the rest of the question, because we haven't actually answered what's asked, which is, what is the largest cylinder? Can that? Oh, so I'm like, I wrote can, that can. What is the largest cylindrical can that can be made using this much material? So we found the radius of this thing, but we need to find the volume. You have a couple choices here. You could either plug 2 in straight to the volume equation. That would be fine. So the volume would equal pi times 12 times 2 minus 2 cubed, which is 24 minus 8. That's going to be 16. So 16 pi cubic inches. Or if you wanted to, you could find the height first. You can say, oh, well, the height is going to be 12 over 2 minus 2, which is 6 minus 2, which is 4 inches. And then the volume would be pi r squared h, which is pi times 2 squared times 4, which is 16 pi. Most of the time with these optimization questions, they're usually asking for the dimensions and not for the total volume or whatever. But occasionally they do change it up and ask for what's the maximum volume or what's the minimum volume if you do something else. Okay, we got time. This is a good question. I like this one. All right, let's keep going. This is kind of a classic question that always gets asked, I feel like. What are the dimensions of the largest rectangle? So if I say largest rectangle, I mean it has the most what? Perimeter, area, or volume? Area, right? Because the area is kind of the biggest dimension that a rectangle occupies, right? It doesn't really have volume. So what are the dimensions of the largest rectangle that can be inscribed in a semicircle of radius, let's go 6 inches. And I'm going to show you two ways of doing this, because one is the more usual way, but the math is gnarly, and the other way is a lot slicker, but it's a little less obvious. So let's do it the hard way first. So here is my semicircle. That's pretty good. I'm always pleased when I draw a good circle, a good semicircle. Radius 6. I don't know if I really need to label those, but fine. And here's my inscribed rectangle. And I definitely wanted to touch the corners, or I want the corners of the rectangle to touch the semicircle, because otherwise I'm not getting as much bang for my buck as I could, right? If I made it smaller than that, I could have made it larger. And now here's the thing. Well, in fact, I'm not even gonna say here's the thing. I want to find the area of this rectangle. I want to maximize the area of the rectangle. So the area should equal, well, I've drawn this in this way specifically. So typically if you're dealing with like a circle or a semicircle, it usually makes good sense to draw on the coordinate system where the center of your circle or semicircle is at the origin. And so what we usually do, normally you would be like, okay, my rectangle, the area is like base times height. But what we usually do in this situation is we say, well, this point here is the point x comma y, where I've gone over x and up y. What's the area of my rectangle? Well, the height is y and the base is what? Well, it's not just x, it's actually 2x. So the area of this is 2x times y. And this is a pretty typical way of doing it. Okay, now we need to find a constraint. So the constraint here is a little less obvious, but we're constrained by so the word-wise, we're constrained by the fact that this rectangle has to be inside the semicircle. Picture-wise, it means this point, this corner of the rectangle should be on the semicircle. So if you think about it, the distance from the origin to that corner, that distance is the radius of the circle. So you can say, oh, well, my constraint looks like x squared plus y squared better equals 6 squared. That's what's constraining this here. Or you could just literally say I know the equation of a semicircle is y equal to the square root of 16 minus x squared. Sorry, I said 16, I meant 36. But we are right, we want this rectangle to have its corner on the semicircle. So we know that, oh, if x is 6, y would be 0. Or if x is 1, y would be the square root of 35. Or if x is, something else, if x is 4, y is going to be the square root of 20. So we want to be on that circle. So now here's the thing we're going to try and maximize. Area is 2 times x times the square root of 36 minus x squared. And this is where the algebra and the calculus start to get a little bit nasty. So we're going to take the derivative. Well, first I'm actually going to simplify this before I take the derivative. So I'm going to write it as 2 times x times 36 minus x squared to the 1/2 power. And now we're going to differentiate that. So our derivative, you have to use the product rule. It's going to be 2. So I'm thinking of this as one piece. This is another piece. So it's going to be the derivative f, which is 2, times the other part left alone, 36 minus x squared to the 1/2 power, plus 2x times the derivative of this, which is going to be 1/2 times 36 minus x squared to the negative 1/2 times negative 2x. All right, so you can either simplify this by factoring out 36 minus x squared to the negative 1/2 power, but it might be easier to see in a slightly different way. So I'm going to write it this way. I'm going to write this as 2 times the square root of 36 minus x squared. I can cancel a 2 here and a 2 here. I've got a minus 2 times x, so minus 2x squared divided by the square root of 36 minus x squared. So questions about that? So now I'm going to multiply this part here by the square root of 36 over x squared, the square root of 36 minus x squared over the square root of 36 minus x squared. I'm just right over here. So I end up with 2 times 36 minus x squared minus 2x squared over the square root of 36 minus x squared. Okay, one more simplification. On top, I'm going to get 72 minus 2x squared minus 2x squared, which is minus 4x squared, all over this denominator. And I want this to either equal 0 or be undefined. So there's a couple values of x that make it undefined. X could be 6 or negative 6. Although that's definitely not going to maximize the area, right? If you look at plugging in 6 here, if x is 6, y is going to be 0, and you're going to get a rectangle with 0 area. Or setting the top equal to 0, 72 minus 4x squared equal to 0, you're going to have x squared equal to 18. So x is going to be the square root of 18, which is 3 root 2. I guess it could be plus or minus root 2. Typically, when you look at this, we kind of limit the x values to be positive so that we don't have to think about it being on the other side. How do you get rid of the square root? So what I did was I multiplied by the square root of 36 minus x squared over the square root of 36 minus x squared, so I have to get a common denominator. So then I have 2 times this is 36 minus x squared, and then minus the 2x squared there. And the denominator is the square root of 36 minus x squared for both pieces. So looking at the number line here, again, I'm really going to just cut off the left side and say, well, x needs to be positive because it's the same thing if x is negative. Right. So my number line is looking like the smallest x could be a 0, the biggest x could be a 6. Right? That's kind of our whole domain for x. And we've got this critical point in the middle that's 3 root 2, or the square root of 18. Okay, so I'm trying to see what's happening to my derivative. So I pick something less than 3 root 2, like 1, and I plug it in. I plug in 1 for x, the bottom's always positive, and 72 minus 4 is definitely positive. And if I pick something between 3 root 2 and 6, well, square root of 18 is definitely less than 5. So I pick 5. 72 minus 4 times 5 squared is 72 minus 100, which is negative. Definitely negative there. So yeah, it's a maximum. So we definitely have a maximum at x equal to 3 root 2. So we wanted to find the dimensions. And if we look back, we know that y was equal to the square root of 36 minus x squared. So y is going to equal the square root of 36 minus the square root of 18 squared. That's the square root of 36 minus 18, which is the square root of 18. So the dimensions of the rectangle are, the base is 2x, which is 2 times 3 root 2, which is 6 root 2. And the height is y, which is the square root of 18, which is 3 root 2. Inches. All right. Quick alternative version of how to do this problem. Because there is and most people often talk about this. I want to point out that there's another way to do this, which is kind of slick. I'm still going to label this the same way. So I'm going to call this point xy. This length here is still 6. What I'm going to do, well, in fact, right, so my area is still 2xy. That's x, that's x. But now I'm going to also label this angle theta. I'm going to say, okay, sine of theta is opposite of our hypotenuse, which is y over 6. So y equals 6 times sine of theta. And cosine of theta, which is adjacent to our hypotenuse, is x over 6. So x equals 6 cosine of theta. And then my area equation becomes 2 times 6 cosine theta times 6 sine theta, which simplifies to 72 times sine theta cosine theta. And now I didn't even have to do anything. My function, my thing I want to maximize is already a function of one variable instead of being a function of two variables like it was here. So now I can just take the derivative. So the constant 72 hangs out. I'm going to use the product rule here. The derivative of sine is cosine times cosine plus sine times the derivative of cosine, which is negative sine. I want that to equal 0. So I've got 72 times cosine squared theta minus sine squared theta equal to 0. So I essentially need cosine to equal sine. What's the angle where cosine equals sine? Exactly. So my critical value is theta equal to pi over 4. Now, I want to point out that the way I've drawn this, the smallest angle that makes sense is 0, right? If the point's over here. And the biggest angle that makes sense is pi over 2. If the point's over there. So if we're trying to find if it's actually a maximum, our critical value is pi over 4, and the smallest value would be 0, and the biggest value would be pi over 2. Okay, well, let's think about this for a second. If you pick an angle bigger than pi over 4, like say pi over 3, cosine smaller than sine. So it's going to be negative. Pick an angle smaller than pi over 4, like pi over 6. Cosine is bigger than sine. So that expression is going to be positive. So we do have, in fact, a maximum. Great. So now the base is 2x, which is 2 times 6 times cosine of pi over 4. Pi over 4 is my angle. And cosine of pi over 4 is root 2 over 2. That's going to be 2 times 6 times root 2 over 2. The 2's cancel, and you get 6 root 2. Just like we did right there. The height is going to be just y, which is 6 times sine of pi over 4, which is 6 times root 2 over 2, which is 3 root 2. So you get the same answers.